Kia ora, Year 11 and 12. This is question 3 from last year's Level 2 Calculus paper. The video is going to be a little bit longer than usual, sorry. It's because I don't want to split up question 3C, which is a kinematics question with 3 linked parts. As usual, give the questions a go before you watch me do them. Right, so the first one, we're given the gradient function for a curve, and this is it here. And the curve passes through the point 1, 0. And the gradient is a parabola, quadratic, so we know our answer should be a cubic. So y will equal x cubed minus 5x. So all I'm doing to get that is I am anti-differentiating this 3x squared minus 5 dx. And I mustn't forget that on the end of that I have to have the constant of integration plus c. Now I use this piece of information to pin down the plus c, so I know that when x is 1, y is 0. So 0 equals 1 cubed minus 5 times 1 plus c, so 0 equals negative 4 plus c, c equals 4, so y equals x cubed minus 5x plus 4. Right, on to the next question. This is one of these ones where you've got to draw. This time you're given the gradient function and you've got to draw the function. Be really careful to read that carefully. I've seen quite a few students in the last couple of years go the wrong way around and differentiate. So we need to anti-differentiate. So this one down here will be a cubic. And before I start drawing anything, we're going to take a wee look at the two types of cubics and just think about their gradients. So here's the first type, and here's the second type. Now this second one down here is what we call a positive cubic. So for example, y equals 2x cubed da 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 da. This one up here is y equals negative 2x cubed da da da. So this is a negative cubic. Let's have a look at the pattern we see with the gradient function for the two of them. So here, the positive cubic, what have I got? Well, I've got a positive gradient here, and I've got a positive gradient here. And I've got a negative gradient in the middle. So let's take a look at what we've got in our gradient function and see if that pattern fits. Well, here's the positive bit. Positive gradient for those values, and positive gradient for those values. Negative gradient in here. So the gradient function that I've got has come from a positive cubic equation. So this is the shape we want. There are a couple of key values we've got to get right, as well as getting that pattern for the shape of the graph. So at x equals 1, 2, 3, 4 little squares, I'm going to have a local maximum. And I can stick that on wherever I want, but it's got to be a maximum. I'll put it there. And at 2 little squares for x, I'm going to have a local minimum. And again, I can put that anywhere as long as it's lower than the local maximum. Otherwise it doesn't make sense. Now I'm going to draw in the cubic. Let's see how we go with that. Whoosh. Pretty good. Okay, the other thing to note is that this point here is where the slope, the gradient, stays negative. So here the gradient moving down here gets to its most negative value. So its steepest negative bit is there. It's still negative here, but it's getting back closer to 0. And we call that a point of inflection. So there it is there. Okay, so that's a positive cubic that you've drawn, and again, two key things there are these values here. And so now we're going to move to the kinematics questions. Right, this one is about me riding her motocross bike, and you can see straight away there's a V for velocity, and there's A for acceleration, and there's a bunch of questions. So just going right back to the start with kinematics, what we're doing is we're linking up displacement, how far we've travelled from a point, velocity, which we generally think of as speed, and acceleration. to move from S to V to A, we differentiate. And to go backwards, we antidifferentiate. So the hardest thing with these problems is working out the setup. And in this case, Meg is passing a fixed point P, and she's got velocity of 5 meters per second. Right? And we're told her acceleration. First question is, if she keeps accelerating at this rate, right, so those words are important, what's her speed when she's been going for 10 seconds after passing P? So what we're looking for is V at 10 seconds. That's our goal. But to get there, we've got to do a bit of calculus. That's really, really important that when you do kinematics problems in a calculus exam in New Zealand, that you show that you're using calculus. So don't just dump in formulae that you know quite well from physics. Okay, so you'll see what I mean. So to find velocity, we're going to antidifferentiate like this, because we know that her acceleration is constant. Okay, so V of t is equal to 0.6 t plus c, and when t equals 0, we have V equals 5. So 5 is equal to 0.6 times 0 plus c, so c equals 5, right? So some kind of working like that to show that c equals 5. That gives me my equation, V of t is equal to 0.6 t plus 5. And now I'm going to substitute in 10, so we get V of 10 is equal to 0.6 times 10 plus 5, which is 11 meters per second. So that's that first question done. I'll just have a look and see if that was achieved or merit. That's merit. Okay, so you don't need the units, but you should put the units, right? We're doing kinematics, so we check on my unit of time, which is seconds, and we check that I'm doing velocity, so it'll be meters per second. Okay, we could also write that as 11 ms to the negative 1. Okay, so the next question is, how far will she have gone from P when she reaches a speed of 8? So when V of t is equal to 8, we have to find S. So what we've got to work out first is how long is it going to take her to have her speed be 8 meters per second. And to do that, we're going to be solving this equation here. Then we need to work out our equation for displacement. So to do that, we're going to anti-differentiate the velocity equation. Okay, so there's just a couple of wee steps. This is an excellence problem, but it's actually, I don't think, too hard if you break it down. On the next slide, we're going to do that slowly. Okay, so remember, V of t was equal to 0.6 t plus 5. We want to work out when her speed's 8, so this is what we do. We solve that equation, 3 equals 0.6 t, and we get t is equal to 5 seconds. So after 5 seconds, she's doing a speed of 8 meters per second. Now we need to substitute that in to S of t, but we don't know what that is yet. But the displacement equation always comes from anti-differentiating velocity. So that's going to give me 0.3 t squared. Right, so you can check that back, that when I take the 2 and I plonk it down onto the 3, it all works. So 0.3 t squared plus 5t and plus c again. Now how am I going to get the plus c? Well, I know that I've defined time to be time since she passed her starting point. So at t equals 0, S equals 0, therefore 0 equals 0 plus 0 plus c, so c equals 0, right? So what I'm doing here is a pretty bad, lazy job of my substitution. But I'm again showing that I'm using calculus to get that constant of integration. So that gives me a displacement equation. S of t is equal to 0.3 t squared plus 5t. Okay, now what I have to do now is to say, when is she going at a speed of 8? And remember, we've done that bit of work up here, so my next step is now to substitute t equals 5, and we'll do it on a new slide. Alright, so s of t is equal to 0.3 t squared plus 5t. S of 5 is equal to 0.3 times 5 squared plus 5 times 5, and that works out to be 32.5 metres, right? My unit's metres because S measures displacement. So that's how far she's gone. So that's all good. Now we've got one last little bit about her friend Leo. Okay, Meg's friend Leo was riding with her, but he begins to decelerate when they get to a speed of 8 metres per second. Now, if he decelerates at 0.2 metres per second squared, how far past point P will he be when he reaches a speed of 6 metres per second? So let's think about what we've got already. Well, we've had, here was point P, and we know that after 5 seconds, t equals 5, velocity equals 8. So that's good, because this is the point where he starts to slow down, right? She keeps on going. So velocity is 8 after 5 seconds, and we know that they've gone 32.5 metres so far. So now what we're going to do is we're going to call this, think of this as P dash, and we'll just start a new little problem and say that, well, he's slowing down at an A of, so A is now equal to negative 0.2 because he's decelerating. And he's going to go some way along here, and we want to know how far he's gone when his speed is down to 6. So we start again and we say, what's V of t? Right, so t is now equal to time since he was at P dash. Right? Now you don't have to write that down, but it might help. So velocity we get by anti-differentiating this. So what do we have here? Well, anti-differentiate that one, and we get negative 0.2 t plus c. Now we know that when t equals 0, right, so t is now equal to 0 here. This is my new t equals 0. So thinking now about what's going on, we've got 8 equals negative 0.2 times 0 plus c. So c is equal to 8. And we're going to pop that back into my velocity equation. Alright, so v of t is equal to negative 0.2 t plus 8. And we want to figure out when does his speed get down to 6. So when is v equals 6? So we're going to solve 6 is equal to negative 0.2 t plus 8. Negative 2 equals negative 0.2 t. T equals 10. So after 10 seconds, we want to figure out how far he's gone in the 10 seconds since he slowed down. So we've got 32.5 metres just plonked in there, and then we've got this distance here, which is s of 10. Now we had our velocity equation, so my displacement equation I get from anti-differentiating that, and that's going to be negative 0.1 t squared plus 8t plus c. Right, now we'd better figure out the plus c again, and we know that at that starting point, how far had he gone from P dash? He'd gone nowhere, so s of 0 is equal to 0. So 0 equals 0 plus 0 plus c, so c equals 0. Right, so finally we've got s of t is equal to negative 0.1 t squared plus 8t. Now we're substituting in 10 because that was the time value that gave me velocity equal to 6. So S of 10 is equal to negative 0.1 times 100 plus 80. So that's 70 metres. So that looks good, that number makes sense. Let's think about what we've got going on. Well, we started off at point P, where they were both biking together, and after 5 seconds, they had covered 32.5 metres. Leo slowed down at that point, and by the time he got to 10 seconds from the slowdown point, so we've got 2 time scales going on here. So in those 10 seconds, he covered another 70 metres. Right, so the total distance from point P is equal to 102.5 metres. Okay, please leave me a comment or come and see me in class if you've got any questions on that one.